Computer. Right. Hello, everyone. And today we're going to talk about motion in one dimension. Effectively, that's movement in a straight line. Okay, so obviously movement is almost never in a straight line, but in some cases it's quite straightforward. Example, a person running 100 meters, they run in a straight line, or a lift going up and down, moving in a straight line. Typically, a car traveling from on a straight section of road, obviously moving in a straight line. And even if the car doesn't move in a straight road, we can also always approximate, like say, well, imagine if it is. I mean, it doesn't really matter if the road is wiggly or not if we're talking about a car traveling 100 miles. Anyways, so let's start with a simple thing. Or what is an equation of motion? So an equation of motion is an equation that tells you where something is at any given time. Okay, I'll share the whiteboard, by the way. Copy. This is the whiteboard. You can follow me on the whiteboard. An equation of motion is an equation that shows you the position of an object at any moment in time. Oh, it doesn't necessarily have to be position. Sometimes it's the velocity, but typically when we say equation of motion, we mean position. It's an equation that tells you where something is at a given time. So how does that work? Well, an example would be let's say a runner running at constant speed 3 meters per second. Right, and let's say we have an x-axis, and this is the 0 on the x-axis, and the runner starts from 0, and they run at 3 meters a second. After t seconds, the coordinates, the position of the runner is 3 multiplied by t meters. So after 1 second, it's 3 meters. After 2 seconds is 6 meters. After 3 seconds is 9 meters, etc. Right? So that's the equation. We say x of t is 3t. And that is what we call an equation of motion. Imagine we have another runner. So that's the position of runner A. Let's say we have another runner starting at 21 meters and running at 4 meters a second. At 4 meters a second, but backwards. So it's minus 4 meters a second. So after t seconds, the position of runner B, this is runner B, is 21 minus 4 times the time, right? So after 0 seconds is 21, after 1 second is 17, etc. So we say x of t is 21 minus 4t, and that's also an equation of motion for runner B. So this is for runner A, and this is for runner B. Equation equation of motion. And we can sketch those. They have graphs. So we can say we can go to Desmos, for example, and draw one. Well, x equals 3t. Okay. That doesn't make any sense. Okay, y equals 3x. Let's put it easy. And y equals 21 minus 4x. And of course, time is positive, 0. X is 0. Okay, so you can see the two graphs of motion. These are the equations of the graphs of motion. So you can see that runner A starts at 0. This is runner A. And every second, they travel 3 meters. So after 1 second, it's 3 meters. After 2 seconds, it's 6 meters, etc. And the second runner starts at 21 meters. So they start 21 meters down the line and they run backwards. And every second, they travel 4 meters. So 21, 17, etc. And you can see that they meet after 3 seconds. They meet after 3 seconds. Okay, so I hope that makes sense. So if you're given an equation of motion, it's like x of t. So position at given the time, right? So position is 3t, and xb of t is 21 minus 4t. So if t is 2, for example, then x a of 2 is 6 meters. So the position of runner A after 2 seconds is 6 meters. The position of runner B after 2 seconds is, 421 minus 8, which is 13 meters. Okay, so I really hope that makes sense. And a question to everyone. Do you think you understand what an equation of motion is on a scale of 0 to 10? In the chat, please. So 10, I understand completely, and 0, I don't understand. Let's put it that way. I have no idea what you're talking about. So give me a vote, please, in the chat. Pretty sure the chat is open. Okay, yes. Right. Lovely. Okay, good. Then let's talk types of motion. Well, types of motion, we will consider very importantly uniform motion. It's motion with constant speed in a straight line. So uniform motion, constant speed in a straight line. Uniformly accelerated motion. Uniformly accelerated motion. So this is this is motion with constant acceleration. So that's constant acceleration. We will talk about acceleration a bit later today. Well, then we have uniform circular motion. Uniform circular motion. This we'll study in year 12. Motion. So in a circle. Motion, constant speed in a circle. Constant speed in a circle. Simple harmonic motion. Harmonic motion. This is oscillations, such as a child on a swing. Go bring. That's simple harmonic motion. It's oscillations. So, for example, well, child on a swing is not a very good example because they maybe a child on a on a springy toy on the playground. I don't know. Mass on a spring. Mass on a spring. Okay, that would be some example of simple harmonic. So these are the types of motion that you will study in year. You will study these in year 12, and you will study these today. So in year 10. Lovely. So I hope that makes sense. There are different types of graphs that you can draw when you talk about motion. So of course, there's the displacement time graph, and then there's the velocity time graph, and the acceleration time graph. So this is how displacement changes through time, velocity changes through time, and acceleration changes through time, of course. Right, so here we have a velocity time graph, and we need to know, we need to be able to sketch, just by looking at this graph, sketch the velocity time graph. Now, I'm going to use a technique which you probably don't use in school, but nevertheless, so this is time and v, velocity. There are many different ways you can do this. What I will do, I know that the velocity is the gradient of the displacement time graph. Velocity is the gradient. So what I will do, I will calculate the gradient at every single point and then draw a graph of gradients. Okay. Now, let's see. So how does that work? Well, at 0 seconds, so this is the line, and I think the gradient is, so the tangent is roughly this. This is the tangent. And if we find the gradient of that tangent, so that's 2, and that's 0.5. So the gradient is 2 divided by 0.5, which is 4. So at this point, the gradient is 4 plus 4. So at 0 seconds, velocity is 4. That's how I start drawing the graph. So after 1 second, well, could it be 5? Okay, 1 second. After 1 second, the gradient, so if I draw a tangent line here, so how can I calculate the gradient? Well, I can do from here to here, roughly. So that's 0.5, 1.25, and this is 1. So 1 divided by 1.25 is, what is 1 divided? That doesn't make any sense. 1. Of course, this is 1. 1 divided by 0.5. That's 2. Okay, sorry. 2. So that's 2. And 1 divided by 1.25 is embarrassing. 1.25 is 0.8. Okay. After 1 second, the speed is 0.8. The velocity is 0.8. 0.8. Well, this is 1, 0.8. After 2 seconds, well, you can see that after 1.75 seconds, the gradient is 0. So this is 0.8 plus 0.8. This is 0. So after 1.75, so this is 1 second, 2 seconds, 1.75 seconds is 0. Then after 2 seconds, well, let's do 3 seconds. After 3 seconds, so you draw the gradient. Well, okay, not very accurate. Okay, why am I doing that? If I can do a tangent line, like proper tangent line, like this. So I draw a tangent line at this point, like oh, sorry, not very good. Okay, so we find the gradient at this point, and the gradient. So let's say, oh, this is a good point. This is 4, and this is oh, this is a good point. We can draw like this. So this is 1.75, and this is 3.75. Oh, brilliant. That's 2. And then this is from 2.5 to 4, that's 1.5. So 2 divided by minus 2 divided by 1.5. Minus 2 divided by 1.5. Minus 2 divided by 1.5. Minus 1.3. So minus 1.33. So after 3 seconds, the velocity is minus 1.33. So minus 1, roughly that. And you can see that the graph begins to shape. So that's how the velocity changes through time. How much sense does this make to you? Do you understand what I did? On a scale of 0 to 10 again, please, in the chat. So I found the approximate gradient at every point, and I saw how the gradient is changing, right? So gradient is the steepness. So how steep the line is. So the beginning is quite steep, then it gets less steep, less steep, less steep, zero steepness, that means that it's horizontal, and then the steepness increases but downwards. So velocity goes from high, from 2, then it goes down to 0, zero velocity, and then decreases, decreases, decreases. So that's the graph of velocity versus time. um, if you have a straight line gradient, so for example, oh, time displacement versus time. So let's say you start at 2 seconds. After 1 second, your position is 4. After 2 seconds, your position is 6. After 3 seconds, your position is 8. After 4, your position is 10, etc. So imagine that this is a graph of uniform motion, right? And if you find the gradient at every point, but the gradient at every point is the same, right? It's the same steepness at every point, and you can calculate that gradient. The gradient is, so that's 2 and 10, so that's 8, and here is 4, 8 over 4. So gradient is 8 over 4, which is 2, which is plus 2. So that means the velocity here is plus 2, plus 2, plus 2, plus 2, plus 2. The velocity does not change. And if you draw the gradient, the velocity time graph for this situation, it's 2. 2, and it's just a straight line. So 2 meters a second. Of course, and time is in seconds. So after 0 seconds, your speed is 2. After 1 second, your speed is still 2. After 2 seconds, your speed is still 2, etc. So you can see how this works for the basic situation, where the gradient is constant. So this is an example of uniform motion. Uniform motion is motion in a straight with a constant velocity. Problem 2. Now we look at the displacement time graph, and we need to construct the velocity time, the displacement time graph. Sorry, we have the velocity time graph. Now we need the displacement time graph, and we're given that the well, let's say we're not given anything. Let's say let's say it's the first time in your life that you see a displacement time graph and a velocity time graph, and you need to work out. Well, we need a displacement time graph. You know what? I will use a trick. Just copy this. Okay, too much. It's only 7 seconds. However, I'll probably need a different scale on the x-axis, but never mind. Okay, so this is time, of course, time in seconds, and this is the displacement time, so S, displacement time, and it's in meters. Okay, so let's try to figure out what's going on with the object. Well, look, for the first 2 seconds, it's accelerating, but that means it's constantly changing speed. Okay. However, we know that distance is speed multiplied by time. So we want to know the distance traveled, but the speed is constantly changing. This is really annoying. Let's take a small period of time. Let's take, well, half a second, for example. Let's just a second. Right. First half second. Of course, the velocity is changing in the first half second, but we can assume that it doesn't. Let's say in the first half second, it's constant, and it's about 5 meters a second. rather than it's changing, we say, well, it doesn't change that much. So we just assume that it's somewhere in the middle, somewhere halfway. And this is 5, and it's traveling at 5 meters for half a second. That means 5 times 0.5, that's 2.5 meters. So in the first half second, it travels 2.5 meters. Now for the second half second, let's assume it's traveling at 15, like this. So rather than, and so it travels for half a second, the speed of 15, which is 7.5 meters, of course. Then for the next half second, it is traveling at 25 for half second. That's what, 12.5 meters. And then for another half second, it travels it. So rather than thinking of it like the acceleration is going like the velocity is changing like this, we're saying, what if it's just like this, right? And in each section, the speed is constant. It's increasing, but it's increasing in jumps rather than it's increasing in continuously. And then for this one, they obviously 17.5 meters. It travels 17.5 meters. And then you can see that it travels at constant speed. So 40 times for 3 seconds, 120. And then we can assume for half a second it travels like this. So that's another 17.5. Another, oh, I think it's symmetrical. Okay, that's 12.5. Then another 7.5 meters and 2.5. Like where does, for example, where does 12.5 come from? Well, the speed is 25 and it's half a second. So 0.5 multiplied by 25 is 12.5. I hope that makes sense. So we kind of replace this graph. Okay, and that's how you can calculate the distance. I just need to estimate the total distance. So that's what 40 7 plus 3, 10, 5, 200. 0.5 is a half a second. So for example, this distance, 0.5 seconds. Okay. Right, so and we start drawing the graph. So we'll just need a different scale. So 200, that's a bit annoying. 200, 1, 2, 3, 4, 5. Okay, that's will have to be 200. This is 40. This is 100, 80, 120, 160. Okay, in half a second, it travels 2.5 meters, so somewhere here. In 1 second, it travels 10 meters, so this. In 1.5 seconds, it travels 22.5 meters. In 2 seconds, it travels, well, 2.5 plus 7.5 plus 12.5 plus 17.5, 22, 30, 40 meters. In 2 seconds, it travels 40 meters. And then after in 1 second, in the next second, it travels 40 meters. 40, 40, and another 40. So that's 80, 120, 160. And then in the next half second, so after 5.5 seconds, is another extra 17.5. So 100 and 70. So somewhere here. After 6 seconds, it travels 22.5. Okay. After another 10. Oh, sorry, somewhere here. Here. Okay, and we can see that the graph is curved, then it's straight, and then it's curved backwards. So it slows down, speeds up. So speeds up, constant speed, slow down, down. Hopefully that makes sense. Like, so what I'm doing is I'm assuming that the speed is always constant. It's always traveling at a constant speed, but that speed is changing in jumps. Like it's like going then a little bit faster, then a little bit faster. Let's have a look at how this looks on the in the assignment. There's an exercise where you need to use Wolfram Math World, and that's called the Riemann sum. So let's take the equation. Let's say t is x minus 1. As x goes from 0 to 4 seconds. Okay, I'm doing this. I'm actually doing the problem. Okay, let's not do the problem. Let's do 3. So 10 plus 6x minus 5x squared. 6. I'm assuming it's about 6 seconds using 10 rectangles. Okay. Doesn't work. Okay, well, let's see if we can. Doesn't work. I don't know. Not sure what happened. But anyways, you can see that here area, the area under the graph is estimated with these rectangles. And that's exactly what you were doing. So you're assuming, so if the velocity is changing like this, like the red line is that how the velocity actually is changing, then you say, well, what if it's just changing in steps? That's how integration works, actually. You will learn integration in year 11 in, well, not in school, but at COMPOS in year 11, you will learn integration. And this is how it's done. You need to find the distance traveled, but your speed is constantly changing. And you're saying, well, what if it isn't? What if it's just a constant speed, and we can find that we can find the distance traveled in that small time. So let's see if we can make sense of it. Okay. Um, right. So you can see that for the first, so this is 0.5, so this is 0.1 seconds. So for 0.1 seconds, the object traveled at 1 meter a second, right? 1 meter per second or 0.1 seconds. So the distance traveled would be 0.1 meters. 0.1 meters. Then you can see that the speed dropped to about 0.9. And we can say, well, that's about 0.09 meters traveled. Then the speed dropped to 0.8, I'm guessing, approximately 0.08. I would say this is 0.06, 0.05, 0.03. So you can actually start drawing the graph, right? Because you know that in 0.1 second, the object it was started at 0. In 0.1 seconds, it traveled 0.1 meters, 0.1. Then in 0.2 seconds, it traveled 0.19 because that's the total, 0.19. 0.3, it traveled 0.27, 0.4, it traveled 0.33, and etc. So you get a graph like this. Does that make sense? What do you think? Can you tell me? Do you understand this on a scale of 0 to 10? A nice 10. Okay. I mean, it's okay not to, because for myself, I think I understood that, yeah, probably somewhere in year 13. Like nowhere. Yeah, it's a really tough challenge to get this. I actually first learned integration and only then I understood what's going on here. But bottom line is area under the graph, area under display velocity time graph is displacement. And the gradient of a displacement time graph, gradient of a displacement time graph is velocity. Okay. Right, so now moving on. Oh, I like this question. A car travels half its journey at 40, half the distance. Half the distance. The distance. At 40 miles an hour, and the second half at 60 miles an hour. What is the average speed? Okay. Anyone brave enough to give me the correct answer? Oh, okay. Very good. 48. It is 48. Uh, well done. Did you know this? Have you done this before? Or are you very quick at doing maths? Okay. Right. So average speed. Average speed is total distance. Distance divided by total time. Right. So let's say we start off a journey, and let's say that the whole journey is 2x. That's the total distance. It's the distance. 2 because, well, we're splitting it in half, so it would make sense to have 2x. And this is x, obviously. The distance is x, and this distance is x. So the time, t1, the time for the first half, is distance divided by speed. So is x divided by 40. And the time for the second half of the journey is x divided by 60. So average speed is total distance, which is 2x, divided by total time. And the total time is t1, which is x over 40, and t2 is x over 60. So x over 40 plus x over 60, and 2x. So we find the common denominator, which is 120, I'm guessing. So 120. So that's 3x plus 2x. And then using the law of division of 2, so 2x divided by 5x over 120. So x cancels, 120, 240 divided by 5, which is 48 miles per hour. Okay, so not 50, but 48. So it's less than we expect. And the reason for that, the car spends more time traveling at 40 than it travels at 60. And that's why answer is less than 50 miles an hour, because you spend more time traveling at a slower speed, Okay. Now, if you're still not convinced, let's consider an extreme case. Imagine someone really clever invented a super fast train that takes you from London to New York. I don't know the distance to New York. 3,000 miles? 4,000 miles? Okay, let's call it New Cork. And it's going to be 1,000 miles. I'm a bit lazy. Okay, 1,000 miles. And you are taking a super fast train one way. And the train is 1,000 miles an hour. Such trains obviously don't exist, but we're talking about an extreme case. And because it's a very warm day, you decide to swim back at 1 mile an hour. So you take a super fast train one way, but then you swim the other way at 1 mile an hour. So let's see what's your average speed? Well, you need to find the time it takes. So time going one way is 1 hour, obviously. The time going backwards is 1,000 hours. Okay. The average speed is the distance divided by the time. So the distance is 2,000 miles, because obviously you go there and back, and the time is 1,001 hours. Well, in physics, we say that 1,001 is pretty much 1,000, right? Like, I mean, who cares about the extra hour? So this is approximately 2 miles per hour. Even though your half the journey is 1,000 miles an hour, and then the Going back is 1 mile an hour. The average speed is nowhere near 500, which an unexperienced person would try to guess. Yes, that is 500 miles an hour is the average speed. Obviously not. It's 2 miles an hour. You're much closer to the lower speed because most of your journey you're just chilling and swimming and yeah. Okay, moving on. Uh, this is one of my favorite questions, and it's also to do with extreme cases, and it's actually a question from I think like a Google interview or something, or like a Facebook interview or whatever, like companies which hire really good problem solvers, such as future yourselves. I don't know, but a lot of you might end up working in tech and going through some of these interview questions. So yeah, runners say that setting up a record on a windy day is almost impossible. So basically, on a windy day, you run slower. And you would think, well, how does that make any sense? Because obviously uh, you run faster with the wind, you run slower against the wind. Shouldn't it just even out, right? So we're assuming a circular track. Well, let's consider a circular track where you go with the wind. Half the journey you go with the wind. So let's say you go that way with the wind, and then v is your normal speed. Normal speed. U, v plus u is your speed with the wind. Speed downwind. Wind. And v minus u is your speed upwind or against the wind. Against wind. Makes sense, right? So you go faster, one way faster, the other one slower. So let's say that one way you go v plus u, you go at a faster speed, and the second half of the loop you run with v minus u. And let's say the whole distance, once again, is 2s. So you go, this distance is s. So total distance is 2s. Distance is 2s. Now, without wind, your speed would be v, of course, right? But with wind, well, no, we would say that the bends are so small that so you just run, you turn around, you run back. Of course, something weird happens in the bends, but we don't care about that. So you just run and then you turn around and you're backwards. Okay, so let's see your total time. So t1 is your time one way, and it's the distance divided by the speed. So s divided by v plus u. Your time backwards, t2, is obviously s divided by v minus u. And then your average speed is the total distance, it's 2s, divided by t1 plus t2, the total time. That's 2s divided by s over v plus u plus s over v minus u. Now, I don't know how well you are or how well you deal with fractions, but s cancels out. Well, let's not do that yet. 2s divided by, so this common denominator is v minus u, v plus u. So v plus u, v minus u, s v minus u plus v plus u. U cancels out. 2v, so that's 2s divided by 2sv divided by v plus u, v minus u. And then we can multiply, so 2s multiplied by v squared minus u squared, 2sv, 2s cancels, and we get v squared minus u squared over v, which is v minus u squared over v. Right, so what do we understand here? So without wind, you just run at your normal speed. Your average speed is just v. But with wind, on a circular track, where you go there and back, the average speed is v minus u squared over v, which is obviously less than v. So your speed on a windy day is slower. Okay. And you have to appreciate how I just used algebra to prove without any numbers. I didn't tell you the distance. I didn't tell you what your speed is, right? So you just I just used letters, and I managed to come to a conclusion that whatever u and v is, then you would run slower. Now, it would help to consider an extreme case, and that's what the designers of this question for the interview, like for the Google interview, let's call it Google interview. I don't know where it came from. It was a long time ago, but if they said, okay, well, what would be an extreme case? Well, an extreme case would be when u equals v. That means your speed downwind is double your speed, and your speed against the wind is 0. Right? So effectively, the wind prevents you from running at all. So that means one way your speed is 2v, but the other way your speed is 0. Right? So in this case, time is infinity. You never reach your average. Your average speed is distance divided by time, and time is infinity. So there's just 0. Your average speed is 0. So it's definitely less than your normal running speed. So quite fascinating, I guess. Yeah. So uniformly accelerated motion and derive. Apologies. Looks like I was in a hurry. Derive SUVAT equations. Well, okay. Going to do some algebra here. I've done this before. I've done in the previous one of the previous webinars. So please watch those if you find this a little challenging to understand. Anyway, so imagine you have a graph of motion, and then it's accelerated motion. So imagine that your velocity is v. This is time, and this is the velocity time graph v. And you start off with initial velocity u, and then your velocity increases to a new value v, and it takes the time is t. Okay. New. So we say that u is the initial velocity. V is final velocity, and t is time. A is acceleration, and s is displacement. displacement. We don't normally write them in this order, so I'm going to rejig them a little bit. We're going to put displacement on top, time on the bottom, and acceleration like this. And that's why we call it SUVAT. SUVAT. Okay. Now, we know that the acceleration is the gradient. Well, acceleration is the gradient of the velocity time graph. Say t time graph. Let's find the gradient of that line. And if this is v and this is u, then this is v minus u. And this is obviously because this is 0 and this is t, so that's just t. So the gradient acceleration is the gradient, which is v minus u divided by t. And if we rearrange this, we get v minus u equals at. And we can write v equals u plus at. And that's the first equation. So I'm going to copy that. Here. Okay. Now, we already discussed that displacement is the area under the graph. Displacement is the area under the graph. The graph, the area under the graph is a trapezium. Trapezium, and the area of a trapezium is 1/2 sum of the bases times the height. So we know that this height is v, this is u. So we have a trapezium. Let's move this. So if we take this shape and just paste it and just twist it around and then just use a different color. This is u, this is v, and this is t. So the area is 1/2 u plus v multiplied by t. So displacement S is 1/2 u plus v times t, which makes perfect sense. Because if you think about it, 1/2 times the initial velocity plus final. If you take the initial velocity plus final, divide by 2, that's the average velocity. So the average velocity. So it's just the average velocity times time. Makes perfect sense. And that's called the second SUVAT equation. S equals 1/2 u plus v multiplied by t. So 1, 2, and then the third SUVAT equation. So what we do is we take the second equation to get third and fourth equations. So we take equation 1 and plug it into equation 2. Take equation 1 and plug it into equation 2. So S equals 1/2 u plus v. Instead of v, we write u plus at times t. So 1/2 2u plus at times t, which is ut plus 1/2 at squared. And that's the third equation. S is equal to ut plus 1/2 at squared. That's what we call a third SUVAT equation. So SUVAT is an equation of uniformly accelerated motion. Note that acceleration has to be constant. And finally, to get the fourth equation, we take from the first equation, we express t. So we write v equals u plus at. So from here, I get v minus u equals at. So t is equal to v minus u divided by a. And I substitute that into equation 2. I substitute into the equation 2. So what do I get? I get s equals 1/2 u plus v multiplied by t, which is v minus u divided by a. So if I simplify that, I can multiply the tops, and that's going to be v squared minus u squared, opening the brackets, and then divided by 2a. So here I get 2as equals v squared minus u squared, or v squared equals u squared plus 2as. And that's the fourth equation. So v squared equals u squared plus 2as. That's equation number 4. Now, what's interesting about those four equations? Well, the first equation does not contain s. The second equation does not contain a. The third equation does not contain v, and the fourth equation does not contain t. Now, there's a completely unnecessary fifth equation, which kind of looks like s equals vt minus 1/2 at squared, but that's an unreasonable equation. You can just use the other form. Okay. To solve a SUVAT problem, you just need to use one of these equations. And that's the beautiful thing about SUVAT. So if you have a uniformly accelerated motion, you just use one of the equations. And to figure out which ones you need, this is the procedure, and it works every time. A particle moves in a straight line with constant acceleration. It passes at point A with speed 8. Exactly 5 seconds later, it passes speed. Okay, so that's the initial velocity. That's the final velocity. This is the time. And the distance s is 70. So we just write down s SUVAT. S is 70 meters, of course. U is 8. V is 23. Acceleration is question mark. And T is 5 meters. Oh, looks like we have, okay, bad example. Let's say that this, okay, let's delete some of the data. It just doesn't make any sense. Bad question. Okay. Let's say we don't know S. Let's say we don't know S. Cool. Oh yes. UVT acceleration. Now, the first equation, you can see that you don't have S. So you need an equation with no S. The equation with no S is A equals U plus AT. That's the first equation. And then you just substitute the values. So you're looking for V, of course, V. You're looking for A, so V minus U equals AT. So A is V minus U divided by T. Now you substitute 23 minus 8 divided by 5 seconds, meters per second. And that's 15 divided by 5, which is 3 meters per second squared. That's the acceleration. Easy. Now for question B, the time taken to travel 40 meters after passing point A. So you write another SUVAT. And now we, S is 40 meters. Initial velocity is 8 meters per second. Now we don't know the final velocity because it's not 23. 23 is a different point, right? Acceleration is 3 meters per second squared, and time is question mark. So we're looking for time. So we have no v, and that is equation 3. Equation 3, S is equal to UT. I'll finish at about 20 past 7, guessing. UT plus 1/2 AT squared. Okay, so S is 40. 40 equals U is 8 multiplied by T plus 1/2 multiplied by 3 multiplied by T squared. Ooh, and that's a quadratic equation. Lovely. We know how to solve these. So let's multiply everything by 2, divide by 3. Do we want to divide by 3? No, not really. So 3t squared plus 16t minus 80 equals 0. I'm going to be a bit lazy. I'm just find my calculator and just solve this. 16 minus 80. And it's about 3.14 seconds. So t is 3.14 seconds. Okay, brilliant. So that's how you use SUVAT equations. I hope that makes sense. Number 7, a ball is thrown vertically upwards from the top of a 60 meters high building with an initial speed of 20. So we have a building and we have a ball that is thrown upwards and then it falls, presumably falls back down. After reaching its maximum height, it falls all the way down past the point, releasing, eventually hits the ground. Cool. Acceleration. So acceleration is accelerating downwards. Acceleration is 9.8 meters per second squared. Find the time between the throw and reaching the maximum height. So for this situation, we throw. This is 60 meters. The time. Okay. So we write SUVAT. S, we don't know how far it goes, and they're not asking. Initial velocity is 20 meters per second. V is, well, final velocity is 0 because when it reaches the maximum height, it stops before going back down. Acceleration is minus 9.81 because it's downwards. Acceleration is downwards, meters per second squared. And t is question mark. So from here, we use v equals u plus at because we have no s. And then we do t is v minus u divided by a, which is 20 minus 0. Sorry. 0 minus 20 divided by minus 9.8, which is 2.20 divided by 9.8, which is 2.04. 2.04 seconds. And we can actually verify that. So, bed projectile motion. Right, so let's have a look. So if we throw something up with a speed of 20, shoot. It takes 2.04 seconds to reach the maximum height. The maximum height is 20.39 above the point of release. So I'm shooting something with an initial speed of 20, and that is correct. Okay, so 2.04 seconds. B. The total time before the ball hits the ground. Okay, so the ball hits the ground when the displacement is minus 60, because it was 60 meters above the ground and now it's on the ground. So displacement is minus 60 meters. U is initial velocity is 20 meters per second. Final velocity, we don't know. Some people say the final velocity is zero. No, the final velocity is not zero because when it hits the ground, its speed is anything but zero. It's quite high. So acceleration is minus 9.8 meters per second squared, and T is question mark. Okay, so we don't have V, so we need the equation with S equals ut plus 1/2 at squared. We substitute everything in. Minus 60 equals 20 times t plus, minus 4.9 multiplied by t squared. 4.9 t squared minus 20t minus 60 equals 0. Solve 3. So 4.9, negative 20, negative 60, 6.09 seconds. So t is 6.09 seconds. That's how long it takes to hit the ground. This is how long it takes it to reach the maximum height. The speed with which it strikes the ground. So now we need to find velocity. So c. When it hits the ground, now we write a SUVAT again. SUVAT. Displacement is negative 60, U is 20, V is, we don't know. Well, V is question mark, 9.8, and T is 6.09. So now in this case, you have everything except V, so you use any equation containing V. So I'm going to obviously use the easiest one, so V equals U plus AT. So usually you have to choose which equation to use based on what the data you have. And because we now have all the data, we can use any equation. So V equals 20 minus 9.8 times 6.09, which gives you 20 minus 9.8 times 6.09, which is minus 39.7 meters per second. Why minus? Well, because it's moving down. Minus because it's falling down. Negative as falling down. Cool. And final question. Sorry, I'm a bit rushing towards the end, but I do want to get through, and I'm limited. I'm short on time. Okay, so a car accelerates uniformly from rest for some time, then immediately decelerates uniformly to rest again. The magnitude of the deceleration is twice the magnitude of the acceleration. The total time of the journey is 36, and the total distance is 540. Okay, well, different approach here because you're not given enough data. So I wouldn't go straight into trying to write it down. I'm going to try to draw sketch a graph. So it's a velocity time graph. So a car accelerates uniformly, then decelerates. So it accelerates, and the deceleration is twice. So it accelerates smoothly and then decelerates rapidly. Okay. So we can already make some conclusions from the graph. So first of all, so the maximum speed, let's call it v maximum speed, and let's say that this time is t. Well, we know the time. We know that the time is 36 seconds. 36 seconds. But we know that this acceleration took twice as long than here. So this would be 24 seconds. 24 seconds. So it took 24 seconds to accelerate and 12 seconds to decelerate because the rate of the deceleration is double. The total distance is 400. Okay, lovely. So distance, total distance is the area under the graph is 540 meters. It's the area under graph. But the area under the graph is it's a triangle, right? It's 1/2 base times height. So area is 1/2 base times height, which is 1/2 times 36, right? So this is 36, and the height is v. So 1/2 times 36 times v, and we know that this is 540 meters. So now we can divide by 18. So v equals 540 divided by 1/2 times 36, which is 540 divided by 18 is 30. So the top speed is 30 meters per second. It's quite a fast speed. Motorway speed, I'd say. 30 meters a second, actually higher than motorway speed. 30 meters per second. So A, to find acceleration. Acceleration is, well, it's the, we can use the SUVAT equation. Well, acceleration is a change in speed divided by change in time. So that's from 0 to 30. So 30 divided by time, which is 24 seconds. Sorry, it's not a minus, it's just artifact. 30 divided by 24, 1.25 seconds. So 1.25 meters per second squared, not seconds, of course. 1.25 meters per second squared. The car goes from 0 to 30 in 1.25 seconds. That's an incredibly fast car. The maximum speed reached, well, we know it's Vmax is 30 meters per second. We already worked it out. The time spent accelerating, the time spent decelerating, well, yes, is 24. T1 is 24 seconds and T2 is 12 seconds. Right, so that's it. Yes, unfortunately I have to go. And hope this was useful. Hope I didn't lose you on the way. I do have some more webinars on the same topic. Probably slightly different, I think. So you can always go to our webinars tab on our website and watch the other webinars. So you would want to go to all COMPOS webinars, then click on 2024 year 10, and you would see me in the same position. Wow. Okay. Slightly more tanned. All right. So see you all. See you all in I think 2 weeks time for some maths. All right. See you.